But in this reactor, we will try to remove all the fission products. Not right away. There will be several iterations where we remove more and more and more. But this will give us really, really great neutron economy when we remove all those fission products from the salt. And obviously, you cannot do that in a solid fuel reactor. This is something you can only do in a liquid fuel reactor, whether it be molten salt or molten
Well, and you
metal.
say obviously, that might not be obvious to some people, right? But
Yeah,
like
okay.
the solid fuel reactor, you've got like the fuel trapped and captured in solid fuel rods.
Hmm.
And so you can't actually physically remove anything from those fuel rods unless you take them out of the reactor and chop them up and destroy them essentially, right? Or melt them. And then, but in this case, your fuel is already a liquid and you can process out things out of that liquid stream or a slurry
Yes.
stream, right?
Yes. And that is where we started as a company, because you remember I talked about Thomas, the other Thomas in the beginning, who was doing molten salt, and in order to make these salts have very low corrosiveness in a reactor or even in sort of industrial application, you need to remove impurities, and the way you remove impurities from the salt is also the same way you remove fission products. So we've already been training ourselves to do that in the last almost 10 years.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America.
that is willing
But
to
we're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation
We need scientists to design new
and
fuels.
focus on net public
We
benefit
need engineers to invent new technologies. We need
over absurd levels of radiation protection,
entrepreneurs to sell those technologies.
then we will march towards this.
We need workers to operate assembly lines that hum with high-tech,
we
zero-carbon
have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Welcome to another episode of the Fire Diffusion Podcast, where we talk about energy-dense fuels and how they can better human lives. My name is Mark Heineman, and I'm joined today by Thomas. And Thomas, I'm going to admit, I don't know how to pronounce. Is it Thomas Jam or Thomas Jam?
Just Thomas Jam Pedersen.
Thomas Jam Pedersen. There we go. I should have clarified that before we started recording.
No problem. No
We're
problem.
jumping right in. So, Thomas Jam Pedersen, co-founder at Copenhagen Atomics. Thomas, ecstatic to be chatting with you today. It's late where you are, right? I'm in Colorado, and your time zone ahead because you're in Copenhagen, right?
I'm in Copenhagen. It's sort of 8:30 in the evening, but we regularly work this late anyways. We usually have calls with US friends and customers and so on this time.
Nice. Okay. Well, Thomas, I'm stoked to chat with you. We've met once before in Austin, Texas, at one of the Texas Nuclear Alliance summits. Really cool event. But yeah, excited to chat about your background, your guys' technology. You've been around for a while, and so there's lots of public information about what you've been working on. And stoked to hear a little bit more about it. Before we jump into Copenhagen Atomics, why don't you give the audience just a brief background on yourself, your education? What were you doing before starting Copenhagen Atomics?
Yeah, so actually I did part of my master degree at UT Austin, so not very far away from where we met. And I started out my career as an electrical engineer, but sort of before I really finished my engineering degree, I ended up working more on software. I did a lot of mathematical modeling and simulations, things like that. And that's also how I got involved in this project with thorium energy and Copenhagen Atomics. Yeah, so I was part of a number of startup companies throughout my career, mostly related to software. I also worked in Silicon Valley for a while and was involved with Google there. And then I spent most of my adult life in Copenhagen. That's where I have my kids and family and so on. And tonight I'm in Copenhagen. That's where we started the company, because we were three engineers and a physicist that met each other here, and we decided to start the company because we thought that this thorium molten salt reactor technology we had heard about and read about on the internet. We independently of each other, we found out about this technology, and then later on we met each other at an event in Copenhagen, and then we started talking, and eventually it led to us agreeing to start a company. There was some other people involved early on, so it's not only the four of us, but these four people were the ones that kept on investing money and time into the project, and that's why we're now the four co-founders of the company. And really early on, sort of even before we started the company, we agreed that this thorium molten salt reactor would likely be the biggest opportunity in our lifetimes. And between us, we had a lot of the sort of skills that are required to start a company. Two of the people are chemical engineers, so they had a lot of, and especially one of them, Thomas Jam Pedersen, one of my colleagues, he had worked on molten salt and corrosion for many years. He had a PhD in that, so he already had a lot more information than many of the people in the nuclear industry at that time. So that's how we got started. And like I said, my background is electrical engineering and software and mathematical modeling. But I've also been part of a number of startup companies and technology companies. So I guess that's my background.
I love it. Yeah. When you say, let's see, the other Thomas on the team, right? You said chemical engineer. What kind of knowledge did he have that the rest of the industry didn't?
Yeah, so actually he was doing his PhD as an industrial PhD, working with a company here in Denmark that wanted to use molten salt for a completely different thing, not nuclear. But in order to use molten salts in that other technology, I mean, they had to figure out how to avoid problems with corrosion and how to understand the electrochemistry of different salts. And his professor was actually part of the molten salt reactor experiment at Oak Ridge in the 1960s. And then that professor came back to Denmark and started basically that whole department at the university where they worked on molten salt and material science. And he's now 85 years old, but he has also helped us a lot in starting this company. He gave us a lot of great advice in the beginning. He's now retired, but he's been a great help. And other people in that department at the University of, it's called the Technical University of Denmark. They have also been very helpful. And we learned a lot from them in the first 5 years. And as I said, Thomas was part of that department before. That's where he did his PhD. So I mean, he already had 5-6 years of experience by the time I met him with corrosion and how to do electrochemistry and all kinds of other things with these molten salts. And there's sort of a little bit of a fun story because I met him at an event, and he said, corrosion, that's no problem. I know how to fix that. And I was like, okay, I've been to other conferences and I've read lots of stuff on the internet, and everybody tells me that corrosion is a problem and they don't know very much about it. And I was like, he's probably lying. He's probably drunk or something. I don't know. We did drink beer at that event. Anyways, and then a couple of days later, sort of a week later, I decided to, I went down to my local supermarket, just bought some table salt, and I went home to my kitchen, and then I started melting that table salt in a pot in my kitchen. And then I called him up and said, I'm melting salt in my kitchen. And he said, I'm coming over. And then it takes quite a while. So the melting point of sodium chloride is sort of 800, I can't remember, 805 degrees or something like that. So it took quite a while before that melted, and we had also some issues with the heating system. So he came over, and we waited for that to melt for many hours, and then we talked about how all the things he knew about molten salt. And I realized that day that he actually did know a lot. That one day I learned more from him about molten salt than all the other documents I read online. So we started sort of that was even before we started the company. So we knew quite a lot about molten salts and how it works and all the corrosion and how to handle the salts even, really, really early on.
Day one, day zero, real life experiment, right? As simple as it gets. Like, hey, we want to use molten salt. Does it actually melt? Okay, confirmed, it melts. Yeah, that's awesome. Okay, do you want to pitch or kind of give an overview of what you guys are trying to accomplish? I know you've been around for a while, like I said, and have lots of publicly available information. But there's a small chance that someone listens to this and hasn't heard of you before. So let's go ahead and give you a chance to disclose what you're up to. So
Yeah. So we realized there many years ago, 2013, 14, we realized that, I mean, of course, the world needs more energy, and thorium combined with molten salt reactors is a unique opportunity to make very low cost energy. And part of the reason why that's possible is because you can remove the fission products while the reactor's running, so you get better neutron economy. You also have low pressure, so basically atmospheric pressure, so your system can be much smaller, and you know the cost of constructing the system and the requirements to that system is much less than for light water reactors, which are really big, and there's so much requirements on those pressure components, so it becomes super expensive. I think we can build the whole reactor for the same price as a light water reactor. You can buy one pump. It's just completely different scale of costs for these types of reactors. And we realized that really early on. We just didn't know how to actually build a nuclear reactor. We found that out later. And then along the way, we made some good discoveries or great inventions. The onion core is one of them that makes it possible to have even better neutron economy than most other molten salt reactors. We also figured out how to make a ton scale production of very pure salt so that we can build reactors out of stainless steel, which is a cheap material. And then we also invented a pump and lithium-7 enrichment and other things. Yeah, that has taken 10 years, and now we just need to put everything together and build a reactor. It sounds easy, but it'll take a few years.
So you touched on a bunch in there. We can get pretty technical. So you said you didn't know how to build a nuclear reactor, but what do you mean by that?
So, we have 4 people. None of us come from the nuclear industry. Two of them comes from chemical industry and material science. And the other 2, me and Aslak, we've done quite a lot of simulations and things like that. And I've also done sort of mechanical engineering and electronics and sensors, and Aslak has done some of that as well. And we just, in the beginning, we said, okay, how can we build a reactor that can make energy significantly lower cost than any other energy technology? Is that possible? If it's not possible, we don't want to do it. I mean, we don't want to have sort of a new type of reactor that has roughly the same price as a light water reactor. If that's the case, if we're not much better than a light water reactor, then we might as well go do something else. I mean, we have skills, we can do other businesses or working other jobs or whatever. So the first 2 or 3, 4 years, we spent all the time trying to figure out, how can we build some sort of reactor that can generate energy sort of order of magnitude lower price than traditional reactors. And obviously there's different components. There's the cost of the reactor itself, like what does all the hardware cost? Then there's the cost of the fuel, what does the fuel cost and the refueling, and also the handling of the spent fuel afterwards. Then there's the cost of approval, like how expensive will it be to license or approve this type of technology. And then there's the whole construction time, because capital cost is very dependent on how long it takes from you start a project until you start generating energy or revenue. So unfortunately, with some of the light water reactors today, we now see that it takes more than 10 years. And in that case, if it's 10 or 15 years, then the capital cost is like 70% of the whole cost. So basically,
half of that's just the financing, right? Like
exactly. So basically, you get the building and the fuel for free, and what you pay for is the financial cost and the license. That's sort of what a light water reactor is, and that's crazy. Like, why do we make energy systems where almost all the cost is paperwork and finance? That's just
there's a big idiot index
model
on it, right? Like the idiot index, as Musk and his teams talk about, like total cost of a product divided by the cost of raw materials going into it. Nuclear has light water reactors historically at a high idiot index. So
yes. So really early on, we said we want to build one reactor every day. How can we build one reactor every day? Because if we can do that, then the the capital cost is much smaller, financial cost is much smaller. So that would be great. But then even if you can build a reactor every day, right now in the current regime, you cannot approve or get the license to operate that reactor in one day. That's completely impossible. I actually just these last couple of days, we looked up all the reactors that are still operating today in the whole world. Like we had data on sort of 350 reactors, and we had the construction date and the first day of power production for all of those, so we can set up like how long did it take to get the construction and the license of almost all the reactors in the whole world today, and most of those are light water reactors. So the average is 6.4 years. And I actually thought that it was a lot faster back in the 70s, but it turns out that there's still some fast projects in China and other places today. So even today, the average didn't change very much over all those years if you take decade by decade. But of course, there's been some really unfortunate projects that took 20 years. But there's also been a few one that only took 3 years. So the average is, like I said, 6.5 years. And of course, if you build something like now in the UK is now building Hinkley Point C, and Hinkley Point C is the only reactor that has been where the construction has started in the OECD countries, the only reactor in OECD countries where the construction has started after Fukushima or after 2011. And of course, the regulation of that reactor is crazy. And they now estimate that it will cost $62 billion. And I read somewhere that the financial cost or capital cost of financing that is sort of like 70% of the whole thing. So that, and it I don't know. I don't
So
even know
yours
how
is going
long
to be better than that, right? Like,
definitely. I mean, if it's not better than that, we will just close the company ourselves. No need to sort of move on. Hinkley Point C now is estimated to be electricity price of something like $150 per megawatt hour, and we expect to have $20 per megawatt hour. Maybe not the very first commercial unit, but sort of as soon as we start the mass manufacturing. So a completely different price range, and also we can definitely install one reactor every day, but we can probably not get them approved that fast. I mean, I expect, because like first of a kind in any country today, it's more likely to be 4 or 5 years, because if you look at the statistics of all the other reactors, it's probably something in that order. But we as a company, we are strong believers that there will be type approval someday. Type approval, that means something similar to what we have for airplanes. So if you buy a Boeing airplane, it's built in the US, and when it comes out of the factory, it takes off they have a runway right next to the factory, and then it goes to some airport in some other country. You don't need any approval or anything. It just goes to that airport, it lands there, and then it fills up with the paying passengers, children and women and everything. I mean, no license required, but of course there's a very stringent quality assurance process in the factory. And of course, if we want to mass manufacture reactors, we need the same. We need to have a very stringent quality assurance program in the factory, and probably the regulators from different countries need to be allowed to come and inspect that we actually follow those requirements and rules and so on. And maybe they also need to every now and then take a reactor out and say, okay, let's go through all the details and make sure everything was perfect. But that's the hope for the future, that we can sort of, the reactors are just magically approved as soon as they leave the factory, and then they can be installed in a number of countries who've signed up to this like type approval process. But we're not there yet, and yeah, we're not there yet, and it'll probably take more than 10 years to get to that position.
are you guys going to have your own airplane next to your factory? Just take off and airlift your reactors in places and drop them off?
We could do that. So the weight of an empty reactor, when you transport a reactor, it's not a good idea to transport with fuel inside. So you would transport the fuel from a different fuel manufacturing facility on different routes to the reactor site. So the reactors, when you transport them empty, the weight is sort of between 20 and 25 ton. So you can easily put that inside a cargo airplane. That's not a problem at all, and deliver it at some site. I actually saw some futuristic drawing that there's some of these super big airships that can take something like 20 or 30 containers. So we were thinking, okay, let's if you go to the reactor factory and that airship comes down and it picks up 30 reactors, sort of 1 month production, and then it flies over to another country and goes down and delivers the reactors. So maybe it's possible to install all 30 in one day. Basically, you just need to put them into these cocoons. That, of course, the building and the cocoons and the steam turbine, that takes time to build, and that's something that needs to be built locally. But most of that doesn't require sort of nuclear grade. The cocoon is nuclear grade, but the steam turbine is not.
What is the cocoon? What does that term mean?
So the cocoon is sort of the I sometimes say it's a big shoebox where you put the reactor inside, and it's that cocoon or shoebox has walls that are 2 meter thick. The box itself is 30 meters long and 7 meters tall and 7 meters wide. And that's what protects your reactor from airplane crashes and so on. And it's also the radiation shield. So because of those thick walls, that's what keeps the radiation inside. So that you don't.
Is that like standard construction? Like you've got design that like guys could just go pour concrete and build that part themselves, or?
Yeah, so the cocoon is, we will give away the drawings for that. It's made out of steel, but there is some concrete slabs on it to further reduce the radiation. It's made out of regular steel, so there's probably 100,000 factories around the world that could make something like that. Each of those segments of the cocoon is 7 by 7 by 3 meters. So it's something you can construct in a normal welding workshop, and then you can put it on a truck and deliver it somewhere. Of course, it's a little bit wide for road transport, so you need some what is called like road assistance or whatever when you're transporting those
oversized loads in the US.
Yes. But that can be built locally and delivered ahead of time, and it's not very expensive. If I remember correctly, typical cost of the whole cocoon is like $3 million. So yeah, it's a giant shoebox. And then you put the reactor inside and run the reactor for a number of years, and then every now and then we replace the reactor container inside that shoebox, or cocoon. We keep the cocoon for 50 years or more.
Nice. So this is like standard sized reactors, right? Is it what, 25 megawatts, or what's the thermal efficiency?
Each reactor unit that goes inside one cocoon can generate 100 megawatts of thermal energy or 42 megawatts of electricity. So if you want a gigawatt power plant, you just need to run 25 of them at the same site, and they can easily fit inside one building. So you just put all 25 inside the same building. And what that gives you also is something really important, is that no nuclear reactor, even the best ones in the world, cannot run all the time like 99% capacity factor. All nuclear reactors have sort of a lower capacity factor. Most of them, if you look at the statistics, most nuclear reactors in the whole world has a capacity factor between 70% for some of the worst ones, up to 92% for some of the best ones. And actually, US has some of the records of high capacity factor of their reactors. But of course, they've been operated for many, many decades, so and now very reliable. And we should expect that any new reactor like ours or any other new type of reactor will not have capacity factor above 90% in the beginning, probably more like 80% in the beginning. It's not because it's our reactor or anyone else. It's just realistic that they don't have high capacity factor in the beginning. And then after a couple of years or 5 or 10 years of operation, all the sort of little things have been ironed out, and then you can expect something like 90% capacity factor. But in the worst case, like if it's a bad reactor design, then you're probably down at 70%, like some of the reactors that are running today. And you can actually look this up on Wikipedia, all the different reactors and the capacity factor in different countries and so on.
Nice.
And that so when you put many reactors in the same building, then the delivery of electricity to your customer will not hurt too much because not all of them will be down at the same time. I mean, if you have a bad day, maybe a third of them, like 30 or 35% are down, but you still have power that you can deliver. Of course, you can deliver a little bit less power than on a good day when all of them are running. But by having many reactors on the same site, you have a high reliability of the electricity to the customer. And that's also why the classical, like the big light water reactors, they typically build 2 or 3 or 4 units at each site. That's for the same reason, because they want to be able to always provide some electricity to the customer or the grid, even though they cannot guarantee that all 4 of them are running all the time.
Yeah. No, I think it's a great idea. Like the redundancy issue and like N+1 and all the reliability requirements, like having modular, repeatable designs, super smart, and it's good package size as far as electrical output. You said onion core earlier. I know what that is, but I imagine a lot of folks don't. Can you describe an onion core with a thorium molten salt reactor?
Yes. So almost all the reactors we have in the world today, both sort of commercial power plants, but also military reactors, almost all of them are cylinder shaped. So the reactor core is a cylinder, and the fuel rods, because most of them have solid fuel, they use fuel rods that are also cylinders. So it's cylinders and cylinders. And just from physics and math, if you look at that, there's some inefficiencies in using cylinders and cylinders, or inside cylinders. So a better model from basic physics and math is a circle, like a ball. And if you can have the fission reaction happen in the middle, and then you can have some sort of blanket that captures the excess neutrons, this is sort of the most efficient design. But there's been some reactors that had a little bit of that shape in the past, but there's not been any sort of molten salt reactor that were designed in that way. And so we patented that, and then we figured out how to actually build that, because it's of course it's different than all the other reactors. So there's some different requirements in how you construct that onion. And the reason why we called it onion core is because you need several layers. First, in the very center, we have heavy water as a moderator. And then the next layer is the fuel salt, where all the energy is generated. And then the next layer is another layer of heavy water to slow down the neutrons and make the reactor run in thermal spectrum. And then finally, the outermost layer is the thorium blanket. And then in between all of those layers, there's also some insulation. An insulation layer. So because the water is at 80 degrees C and the salt is at 600 degrees C, so you need a little bit of insulation in between. So that's why there's many layers, and because it's round like a ball, there's very little neutron leakage. And because of all the materials are made from something that has a low capture cross-section, there's very little neutron losses to the structural materials. And of course, it's difficult to build this reactor out of some materials that can last. There's a very high level of neutron flux in there, and most materials doesn't last very long in high neutron flux. And that's also why we believe that the best material for a commercial power plant or onion core is the silicon carbide, which is not used very much today in commercial reactors, but it's being tested both for cladding for light water reactors. It's also being tested for cladding for high temperature gas cooled reactors, and it's also been testing for structural material in fusion reactors. And of course, it's very similar to the material used in triso fuel. So it is something that has been tested extensively for more than a decade. But of course, it has not been used yet in a molten salt reactor, so I guess we will be the first ones to use it in that type of application.
In these layers, Thomas, you're pumping like your fuel salt and your thorium salt and your heavy water. Those are being pumped in and out of this, right? Like you've got an inlet and outlet out of these layers.
Yes. Yeah, so all the different, there's sort of 4 different channels or 4 different layers, and they're all pumped different flow rates to extract the heat. Of course, the most, like 95% of the heat is in the fuel salt, so that's the most important one, and that's also the one that we pump the fastest with the highest flow rate. And that's where we extract most of the heat, and that goes to the steam turbine and generate electricity. And then sort of roughly 5% of the heat is injected into the water. And most people think that the heat comes from the hot salt right next to it, and it transfers through the insulation. But that's actually a small contribution. The majority of the heat in the heavy water comes from slowing down neutrons and also capturing gamma rays. So, but yeah, that heavy water needs to be cooled all the time. And the way it works with the heavy water is that we pump in the water at the top, and then it just drains out at the bottom, and it drains directly into the sort of the dump tank at the bottom, and then the pumps pump it back up to the top. So as soon as you stop the pumps, everything just drains out in a matter of 20 seconds or 30 seconds, depending on the flow rate. But really, really quickly, you can dump all the water, and that means, of course, that you like as soon as you drop the water just 1 centimeter, then it's not critical anymore. So you can stop
So
the
the water is
criticality.
acting as the moderator, and
Yeah.
that's kind of your like passive safety of if you stop pumping water, then the water drains out and you go subcritical.
Yes, correct. And it also acts as the sort of control rods. So in a classical light water reactor, you have I don't recall the exact numbers, but something like 25% of all the neutrons are captured by the water. So that's a waste of very expensive neutrons. And then you have these control rods, and you also have these burn up poisons in your fuel that captures another 5 or 10% of your neutrons. So basically, you're throwing away almost a third of the neutrons. And then in a light water reactor, you also have a lot of leakage just going out of the top and the bottom and the walls. So you have a huge amount of neutron waste, and that's what we've tried to optimize for. We only have sort of a 2% neutron leakage out of the core and to the structural material, and then we have some more neutron losses to fission products. But this reactor will also be the first reactor where we try to remove all the fission products. There has been, for example, the molten salt reactor experiment in the 60s. They did remove xenon and krypton. So they did remove some of the volatile fission products, and that did help quite a lot on the neutron economy. But in this reactor, we will try to remove all the fission products. Not right away. There will be several iterations where we remove more and more and more. But this will give us really, really great neutron economy when we remove all those fission products from the salt. And obviously, you cannot do that in a solid fuel reactor. This is something you can only do in a liquid fuel reactor, whether it be molten salt or molten
Well, and
metal.
you say obviously, that might not be obvious to some people, right? But
Yeah,
like
okay.
the solid fuel reactor, you've got like the fuel trapped and captured in solid fuel rods. And so you can't actually physically remove anything from those fuel rods unless you take them out of the reactor and chop them up and destroy them, essentially, right? Or melt them. But in this case, your fuel is already a liquid, and you can process out things out of that liquid stream or a slurry stream, right? So
yes, and that's sort of that is where we started as a company, because you remember I talked about Thomas, the other Thomas in the beginning, who was doing molten salt, and in order to make these salts have very low corrosiveness in a reactor or even in sort of industrial application, you need to remove impurities, and the way you remove impurities from the salt is also the same way you remove fission products. So we've already been training ourselves to do that in the last almost 10 years. So we already have a lot of experience in removing different elements from the periodic table from those salts, and some are easy, like again xenon and krypton, it just bubbles out, and some are crazy difficult. And of course, those difficult ones, we will not be able to remove those live while the reactor's running in the first versions. So I think we will maybe be able to remove those difficult, the difficult fission products are the lanthanides. In the lanthanide group in the periodic table, we will likely be able to remove those sort of in 2035 or something like that. But from the beginning, we should be able to remove more than half of all the fission products, which is already super great compared to all the other reactors in the whole world.
So why is that helpful to remove fission products, Thomas?
Yeah, so again, when you run a nuclear reactor, you need a certain amount of fuel. And when you have a certain amount of fuel, it can go critical. That's sort of depending on the reactor design, you need more and more and more fuel to make it go critical. And then once it's critical, then it can generate energy. And then side effect is that it also generates new neutrons all the time. And you need those neutrons to keep the fission or the chain reaction going. And unfortunately, if you're losing too many neutrons to neutron poisons, which neutron poisons is either, like we talked about before, the water, light water in a light water reactor, that captures neutrons, or the fission products. And as you burn up, you burn more and more of your fuel. You have more and more fission products in your fuel, and that means they capture more and more neutrons. So eventually you get to a point where you lose too many neutrons and the chain reaction stops going. And then you have to unload the fuel and load in some new fuel. And the great thing about our reactor is that it can keep on going because we have so little losses that we actually, the reactor can keep on breathing new fuel from thorium in the blanket. And then you don't need to refuel with fresh enriched fuel or fresh uranium. As soon as it's up and running, it can keep itself going for 100 years or
Got
something.
it.
Yeah.
So better remove fission products, better neutron economy, better fuel efficiency, cheaper reactor, cheaper energy, right?
Yeah. So there are two things that drives the cost. First of all, we don't have high pressure. So that means that the structural materials are much easier. And when there's less structural material, also less capturing of neutrons. But also the fact that we've made this onion core, you can make it a lot smaller. And when you can make it smaller, it becomes easier to manufacture. And also the cost of material is smaller. So all these different things help each other for making it smaller and less expensive. And therefore the energy becomes less expensive.
Yeah. That was going to be my next question. Yeah, what makes it so cheap? So better
So
future.
our onion core, the onion core reactor core, it weighs less than a ton or less than 1,000 kilos. Go out and look at all the other reactor cores. They weigh like hundreds of tons. It's just a completely different scale.
Yeah. Is there? I mean, you're using thorium. Is there other uranium or anything to get the process started and make kind of your first one go critical, or
Yeah.
how does
So
that work?
any breeder reactor, any fission reactor where you breathe fuel, it needs some sort of Kickstarter fuel, and that Kickstarter fuel needs to have enough fissile material there for it to go critical on day one. And thorium by itself cannot go critical. You need some sort of Kickstarter fuel, and in the very first reactors, we will use uranium-235. So basically the same fuel as in all the other reactors, 5% enriched uranium. But we could also use spent fuel or plutonium or transuranics. But that's just more difficult to be allowed to do that from the beginning. But someday in the future, we hope we can do that. But yeah, so we use the same fuel as most of the other light water reactors, but we only need sort of 2.5 tons of that to get the process up and running. And once it's up and running, then we don't need more enriched uranium. From then on, we only need thorium, and we need sort of roughly 36 kilograms of thorium per year per reactor. And just to give the audience some comparison, if you want to load one fuel load into a typical light water reactor, AP1000, something like that, it takes something like 100 tons, something. Some of the big ones take upwards towards 200 tons of fuel, and we need only 2.5 tons. So again, it's sort of a factor of 100 less. I know that we also produce less power per unit, but it just kind of tells you how efficient these reactors are in comparison with the big ones, and that's why it's much cheaper, because it uses a lot less materials in any respect, both fuel material and structural material and yeah, everything.
That's awesome. Yeah. I love you guys are beyond the paper reactor phase, right? Like from day one, testing table salt on the stovetop, like you've been doing experiments and prototyping for a long time. Do you want to talk through some of the hardware that you guys have developed and tests that you've done, and why you're confident about some of these costs and
Yes.
projections?
So again, early on we realized that okay, these reactors can be built out of regular stainless steel, which is not very expensive. It's one of the really wonderful materials that we humans have access to. Back when it was invented,
Doesn't corrode, or is corrosion
well, it
resistant?
corrodes a little bit, but it can easily last for 5 years. So I think one of the sort of misunderstandings with molten salt reactors is that a lot of the old people in the nuclear industry, they have been trained for 50 years in light water reactors, and they know that a light water reactor is so expensive. So when you build one, you want it to work for 50 years, and then after 50 years, you apply for an extension and for another 20 years or whatever. So that's their model in their head, that these reactors need to last for 50 years and more. And then when they hear about the corrosion, they said, this is never going to last 50 years. These reactors are impossible. But I think it's because their model in their head is wrong. Because what we said is that the cocoon and the steam turbine needs to last for 50 years. But the reactor container itself costs something like $6 million. Not 6 billion, but 6 million. So if we can make that last 2 or 3 or 4 or 5 years, that's great. Then we can easily get the economics to be much better than for light water reactors. And that's how we started out. And we know now that we can easily make it last. In terms of corrosion, we can easily make it last for 5 years. There's the other issue is the neutron bombardment. And you know that in light water reactors, the cladding is made out of circuloy. And that circuloy can maybe take the neutron bombardment for 4 years, something like that. And then it needs to be replaced. And the materials in our reactor core, in the very first one, we will also use circuloy actually for the water, the heavy water channels, and so that's a similar amount of lifespan. But with these silicon carbides that I was talking about before, we feel confident that we can get it to 5 years. But we also have to convince the regulator that they will say, yeah, this can work for 5 years. And maybe they will not give us 5 years right away. Maybe they will give us 2 years, and then after 2 years we can apply for extension or whatever. But eventually I'm quite positive that we will get to 5 years for a silicon carbide onion core. And then it needs to be replaced, because then the structural materials has been bombarded so much that they are becoming less they become a little bit weak, or they lose some of their strength, and then you want to stop the reactor before it gets too brittle or too weak.
So would you take that reactor then and just throw it away? Like what do you do?
Yeah,
You go and
it's
replace it?
extremely radioactive at that point. So first of all, we need to clean. So when you have that reactor and you shut it down, then you need to unload all the salts into transport tanks, so that you're ready to move the salt into the next reactor unit. So first we unload all the salts and the heavy water into some other tanks outside of the reactor container. And then there will still be a little bit of residues left, so we need to remove that as well. So there's a cleaning process for that. And then after that, you have sort of an empty steel box made out of steel and stainless steel and circuloy and silicon carbide and so on. And that's still radioactive because it has been activated. All the materials has been activated. So you don't want to spend a lot of money recycling that right away. That's too expensive. You want to put it aside for 20 or 50 years or something, so that it can cool down radioactively a little bit. And then after that, you basically just crush the whole thing, like just what is that
Like
called?
a car compactor.
Compact it into it will have roughly the size of 1 cubic meter when you compact it, and it's made of quite thin material, so it is easy to compact. And then you put it into a big furnace and melt it, just like one of these big steel melting furnaces, and you smelt the whole thing. And then you get basically metal that you can reuse. It's slightly radioactive, so you can not use it for uh, whatever, something close to humans, but you can use it for pilings or new reactors, or there's a number of applications where you can use that slightly radioactive material after 50 years. So it can get recycled, and we humans are really good at recycling metals, so it's not very expensive to recycle it. And then you get some slack on top of when you melt the steel. On top of that, you get some slack, and most of the radiation will be in the slack, and then this slack uh, will have to go to what's it called, low level radioactive waste storage. Uh,
Yep. Which we want to be clear, right? This is low level radioactive waste. So yes, it's radioactive, but it's not. There's different quantities and levels of radioactive waste, right? And this would be low level waste. That it is legal and appropriate to dispose of some low level waste just in landfills, right, throughout the world. Like you can just put it in a dump, and like you don't want it for your kitchen table, but like it's okay to put it in landfill. So yeah. Awesome. What kind of systems have you guys built, constructed? I mean, you've got your fab shop, you're building stuff, right? Like you're
yeah.
prototyping. Yeah.
So we in the early days, sort of more than 5 years ago, we mostly built small systems for testing pumps and salts and heat exchangers and so on. And we still do that. That's still the majority of our efforts, is to build testing systems for components like pumps and heat exchangers. But then 3 or 4 years ago, we also started building test reactors. And again, we did the calculations and we decided we want to build full-scale reactors right away. So the test units we have are the same size as our commercial reactor unit. We haven't built the cocoon yet. We just built the reactor box itself, because we're not working with radioactive materials, but we hope to start.
The cocoon's pretty simple, right? Like steel,
Yeah,
concrete. That's very
yes.
well understood. Like
Yeah.
Yeah.
So we just built the full-scale reactor container, the same size as a commercial one, and then we heat up the salts with electricity. And once it's molten and everything, we pump it around, and we don't use heavy water because that's expensive. So we just use regular water. And because we use regular water, we also know that it will not go critical. There's no chance of criticality, accidents or anything. And then we can do a lot of the mechanical tests that we need to do on a reactor unit. And we need, one thing is to get all the components to be reliable, so that a regulator will say this is reliable. We can approve that. We will give you the license to start the test reactor. That's one important milestone. But another important milestone is someday in a not too distant future, we have to run a commercial reactor, and we want like the very first one to have a capacity factor that is higher than 80%. But in order to get there, we need a lot of iron out all the little things that could go wrong, and you do not necessarily find those if you just want one run test. You need to run many test hours in order to find all those issues that could be a problem, and find solutions, and then test again and see that your solution solved the problem. So that's what we're doing now. We have two test reactor units here at the site, and we're building a third one. And again, they are full scale, the same size as a commercial reactor. But of course, we don't run the chain reaction. We just heat it up with electricity right now and pump the salt around and do the loading and unloading of salt. And we do the starting and stopping and all these things that you need to do many times to find all the little issues here and there that needs to be solved, so that you can have a commercial reactor with high capacity factor from day one. And if we go back and look at light water reactors, the reason they have been so successful is because they were able to get them to work quite quickly back in the 50s. And if we look at sodium cooled fast reactors, is another type of reactor that we've built more than 20 of those in the whole world. And especially Russia has spent huge amount of time trying to get them to be stable. But there's none of those reactors that ever got to 80% capacity factor. None of them. None of those 20. And most of them were so expensive to operate that it was just impossible to make them commercial. There's 2 reactors in Russia that are sort of, I think, somewhat commercial, but even Rosatom that are running them, they say that they're much more expensive than the light water reactor that Rosatom is selling, the VVR type reactors. And Russia has 50 years of experience running these sodium cooled fast reactors. So I mean, that's something to remember if you're a reactor designer. If it takes a government with lots of funding more than 50 years to reach even 80% capacity factor, and they're not there yet, and they openly admit that these are much more expensive to operate than light water reactors. Think about that when you want to invest in fast reactors. And it's the same with molten salt reactors. I mean, we are not at the point where if we were to deploy these reactors today, we would not get 80% capacity factor. But that's why we run all the tests, because it's not very expensive to run tests with the when you don't have the chain reaction running, because everything is a lot easier when there's no radiation.
So what's your forecast, Thomas? Like, when will you have these ready to
Yeah, so right now
be
we're
at your
going
80% capacity factor and running commercially?
Yeah, so the first step is to get the first test reactor up and running. And right now we're going through the approval process with the Swiss authorities and the Swiss national lab called PSI, or Paul Schier Institute, because that's where we want to run the first test reactor. That's only a 1 megawatt reactor, so it's still the same physical size, but the pump rate, or the speed of the flow rate of the salt, is much lower, so we only generate small amount of energy, and that's again to make it easier to get the first approvals of the first license. So that first one we expect to run in 2027, and then after that we will likely run another test reactor to test more things, some of this fission product removal and all these other features. But then we will also start the process of getting a license for a commercial reactor. If you look at all the commercial reactors in the past, it will likely take 4 years or more to get a license for a commercial reactor. So while we're waiting for that, or going through that process, then we can keep on testing some of these test reactors at lower power and lower risk. And then, I hope we get the first license for a commercial reactor in 2030. And then we can start operating that. And I'll not guarantee that the very first one has 80% capacity factor, but we definitely want to get above 80% quickly, so that investors can see that this is not something that will take 20 years to commercialize. They can see, okay, there's light at the end of the tunnel. Every year they get 2% extra capacity factor, or something like that. And of course, as soon as we can get above 90% capacity factor, then we have really, really good economy or electricity prices.
Nice. Okay, so 2030 for first commercial license, 2027 for first prototype. You're actively manufacturing stuff. I imagine you're still designing for prototypes and manufacturing for prototypes, but like if you get to that 2030 and you've got the first system up and running, and that's when it gets hard, right? Like scaling up for manufacturing. What's to be thought forward on that?
Yeah, that's very expensive. If you
one reactor per day, right?
Yeah, so at we have a quite big site here. The workshop we have is 100,000 square feet, and at this location we can run sort of 5 test units or 5 test reactors at the same time next to each other. I don't think there's a lot of nuclear companies anywhere in the world that can run 5 units right next to each other. And then at this site we can also build the first 10 commercial reactors. Of course, they cannot be turned on here. We need to move them to another site for actually deploying them and making energy. But we also have enough room here for the fuel manufacturing, because we need to make the thorium and uranium fuels, and also the lithium separation. But we have enough room to do all of that here in this building. So this building, we can get started. We can make all the fuel and all the tests we need to make, and we can build the first 10 commercial reactor units and ship them somewhere and install them and prove that they're running. So I think we're in a good position right now to keep on moving and building more and more. And like I said before, we already have 2 units that are operating, and we're building a 3rd one now. And we also get better and better at ordering these components for a reactor unit. And I think this 3rd one that we're building will take more than a year to order and construct and so on. But I think before we get to 2027, we can order these and build them in less than half a year. And then by the time we get to 2030, I'm confident we can build each unit in less than a month. And that's basically, I mean, that's a little bit what we want to do in the Gigafactory, this production facility where we can make one every day, because there's sort of we have a rough idea of 30 steps in the factory. So every day a reactor go to the next step and get the next components installed, or they need to do some quality assurance or something. But there's sort of 30 steps, so that means it takes 30 days to make the reactor in that factory. And then if you start a new one every day and move it down the line, then you can make one every day. So essentially we would be able to do that already from 2030, but the amount of capital that you need to invest to have the just-in-time supply chain for all the components is quite large. And I don't think any investor would invest that amount of money on the same day where you start the first commercial reactor. So we probably have to wait a couple of years before the investors are willing to put down $10 billion just to basically set up the Gigafactory and all the supply chains for that. But I don't think that will be a limiting factor. I mean, of course, we have to wait for the capital to be ready, but I don't think there's any limiting factor on that in terms of deploying this technology. I think the main limitation will be the time that it takes to get approvals. If you look up in most countries of the world, it takes 4 years or more to get just to get a site license. So that's only one of the nuclear licenses you need to build a commercial reactor. And the site license is sort of almost the same no matter what type of reactor you want to build. It basically just tells you that all the environmental approvals is in place and the local municipality is happy and you have thought about evacuation.
We're cutting that down to 10 months over here in America.
Yeah, let's see. It has never happened before, but I hope it can
18
be done.
months from the NRC, and Uncle Chris says 10 months. Bring it on by July 4th, 2026. Let's go. So setting a standard.
Yeah. So I used to live and work in the US, and this is one of the things I love about the US. This sort of craziness in the ambitions. And if you set the goal by 4th of July next year, you might actually be able to do it in 2 years. I mean, who knows?
Exactly, right? Like, it's a catalyst to say, like, well, everyone's complaining about regulations. Let's get the regulations out of the way. Let's go.
Yeah.
Like, let's go build it.
So one of the things that will be difficult for, the US selected these 10 reactors or 11 projects or whatever it was for this 4th of July goal. And one of the problems is the fuel. I mean, it'll be immensely difficult for these 10 projects to actually have the fuel ready in 12 months. I mean, they could probably build the reactor core and do many of the other things if you have enough resources at least, and write all the documentation and so on. But getting the fuel supply ready in 12 months is really difficult. I mean, some of them are using triso fuel, some of them are using molten salts, and let me think what else. I think there's some high temperature reactors as well. I actually forgot exactly who is on the list, but none of these fuels are readily available, and there's always a lot of regulations around handling this fuel. So that's where it becomes difficult. I mean, you can always weld something, or I mean, yeah, but I really hope some of them makes it.
Yeah. We're all rooting for them. So let's talk capital. You said it's going to take a lot of capital. how, and you said the word billions, so that's it's a standard metric or order of magnitude for in the nuclear space, but like you got to get to millions and then tens of millions and then hundreds of millions before you get to billions. So how are you guys thinking about capital? How much capital do you need along the way? Like, can you talk about this? And
Yeah.
are you fundraising? And
Yeah, we are fundraising and we have been for many years. We have sort of a number of rounds that we have gone through over the years. And again, right now we are racing around and we have some investors that are going through due diligence and
so if folks are interested, they should reach out to you.
Yeah. So the Copenhagen Atomics may be a little bit different the way we fundraise than some of the other companies, but we do it this way that we allow smaller investors to invest sort of 100,000 euros upwards, sort of all the time when they contact us and say, this is a great idea, I want to invest. If they can invest more than 100,000 euros, there's special rules in the EU that then they are called a professional investor, and then we can allow them to invest. If they're smaller than that, it's more complicated. But so we continue to take in investments from those. I won't call them small investors, but they are. I mean, they're not investing billions.
Six-figure checks from still accredited investors.
That's pretty good.
Yeah.
So we have a continuous flow of those types of investments, and then we also talk to bigger investors who can invest 50 or 100 million or like much larger checks. But of course, that also takes more time to close those. And for the test reactor in Switzerland that I mentioned before, we need a total of sort of 200 million euros to do all of that project, all the R&D, all the fuel production, everything, and we will not raise all of that in one round. It's sort of we collect that over several years, but I'm confident we will be able to raise that. And then you talk about sort of the next steps, the mass manufacturing and the commercial deployment, and that's where we're talking billions, of course. Sort of if you look at some of the other reactor projects in the world, then we talked about the Hinkley Point C a little bit earlier. I said 62 billion. That's really expensive, and of course that's government funding, and there's no way we can raise that amount of money. That's only for governments. But if you look at some commercial projects in the energy sector, for example, oil drilling rigs or oil and coal and gas projects, many of those are 2 billion to 10 billion. That's a very typical range for those types of projects. So there's many people or many investors in the energy sector that are used to investing that amount of money. Of course, this is a little bit different because it has a higher risk in the early days, but then it also has a much higher upside in the long term. So the profile of the investors may be a little bit different, but it's not uncommon for investors in the energy sector to look at these types of investments. And I have some other great news for the investor is that if you're able to provide a lot of cheap energy in a country, then that country can manufacture. So all products that we use in the whole world, all products needs energy for manufacturing and transportation and so on. So if a country is able to get cheap energy, then they can make their products a little bit cheaper than the other country next to them, and then they can export a little bit more, and that means that they have a positive, trade balance, and this means that it's a healthy economics, not like these debt countries, and that attracts capital. So a lot of capital wants to invest in the countries where everything is positive and where there's low risk. So that means that if there's a lot of capital wanting to be invested in a country where everything is working well, then the interest rate of capital goes down, and this means that you can build out new industries and new factories and everything faster than in the other country that has bad trade balance and expensive energy. And I'm saying all these things because it's actually a symbol of what's happening right now in Europe. Europe has done all the wrong things, and not just a little bit, like really badly. Like we have We have energy prices that is twice as high as in other countries, the US or China or India. We have really bad regulation that makes everything more expensive. We have high salaries for the employees, and the trade balance for most of the European countries is just horrible right now, especially the big countries like France and Germany and UK. The Scandinavian countries are doing a little bit better. My own country, Denmark, still have a positive trade balance, and of course Norway with all the oil have a very positive trade balance, so that helps. But there's most of the countries in Europe has a bad negative trade balance and very high energy prices, and that just means that capital is just running away from here. It just, no investor want to invest in that environment. So those countries are not going anywhere for sure.
Yeah.
But that's actually one of the things that is more positive in the US, because the energy prices are low, and actually the growth in the US is much higher than in Europe, and also the GDP per capita is much higher, and while the US is still making huge amount of money from all the tech in the old tech industry, and when I say old, I mean all like Windows and or Microsoft and Intel and Facebook and Amazon and Google and Nvidia and all these companies who really thrived on the tech boom of the last 30 years. Europe has none of those countries companies. Well, we have one, the what's it called, AMLS, the semiconductor company in the Netherlands. So we have one, but US has 50 companies like that. So US is still making a lot of money from that old tech bubble, and now US is investing that into the new tech bubble, which is AI, and Europe is also about to lose out on the AI tech bubble and every other tech bubble. It's just, honestly, it's a horrible environment. But we as a company is a little bit different because we cater not to the European market but to the global market. And I think I've said this many times before. I think 80% of all the reactors we will ever build will be installed outside of Europe. So our main market is not Europe; it's outside of Europe, and probably the first gigafactory where we mass manufacture these reactors will be outside of Europe. Yeah, but let's
Yeah,
see.
I was going to ask, are you going to from your past 2 to 5 minute description, like you should move your headquarters to Denver, right, or Cheyenne, Wyoming, or
Yeah,
Austin, Texas, or Huntsville, Alabama, like.
but I mean, we did think about this 5 years ago, and we looked at the NRC 5 years ago, and we said, this is high risk, like really, really high risk. Can we get a reactor approved and get it through the NRC in a reasonable amount of time and a reasonable amount of cost? And we looked at NuScale to spend, I don't know, like more than $1 billion to try to get something approved. And we decided that NRC in the US was a high risk. But I think this has changed in the last year. It's quite different now than it was. But now we're already going through the approval process in Switzerland, and we feel that that's a good route for us.
Yeah.
For right now.
Well, hey man, manufacturing facility in Houston, like that's where I'd build it if I were you.
Maybe that's a good idea. It's not a good idea to build it in Europe. I have this in my head. Maybe I'm a little bit, I'm an engineer, right? So in my head, I have this image of this, cartoon where they're running off the cliff and they don't fall down until they look down. And I think this is what has happened to Europe. Europe has already run off the cliff, and only a few, like 1% of the people in Europe has looked down, and we are very scared because it's very far down. But 99% of the people here, they are not looking down, and they just think it's great.
They can't feel the drop. Yeah.
No,
yeah.
But it's coming. It's coming.
So okay, well let's. I love that cautionary tale, and how does that change? How does that pivot? How do you? I guess if you guys are exporting reactors to places, then you're generating wealth and adding to GDP, right? Like, so that's a positive step.
Yeah, but let's understand that most of our investors already today are not from Europe. They're from the rest of the world, Middle East and US and so on. And eventually, I mean, we developed the first technology here, but eventually most of this company and most of the employees and most of the gigafactory will be outside of Europe. And then, of course, if we have an R&D team here, they will still be paying tax here and providing for the GDP. But in the end, if we don't start making reactors that make low-cost energy in Europe, it won't really change anything. Really, what we need to install 10,000 of these reactors that Copenhagen Atomics have developed in Europe, and use that energy for something that can generate value for people. And some of those products have to be exported. And this, nobody wants to do that right now. But
Well, let's go do
someday,
it, Thomas.
someday
Yeah,
when
yeah,
I talked about this cartoon where they start dropping. When people start really dropping, then they will wake up and say, "Shit, what can we do? Okay, we can
yeah.
install some of these Copenhagen Atomics reactors." So I think the environment will change, but it's in my best estimate, it's more than 5 years away. I hope that in the US we will see the LNT and LR getting sort of changed to some extent.
Yeah.
And I hope that we see the
They ignored,
NRC and being able to
right.
approve things in 2 or 3 or 4 years, so that the US can compete with, I don't know, for example, UAE and Korea and China. So I hope that's what's going to happen in the next 5 years. And then in 5 years from now, Europe will be basically, when you get slammed in your head, you sort of wake up and, oh shit, I have to do something. That's what Europe has coming for it. And they will wake up when they hit the rock bottom. And then they will probably also see we have to do the same as in the US. We have to cut all this crap and red tape. We have to allow these reactors that by then they will probably already be running somewhere else. So they will see, they already work over there. Can we just copy it over here? And then, by 2035, hopefully we can have many reactors running here. But yeah. So actually, your listeners should know this. So if you look at the whole world, the GDP of the whole world, then the BRIC countries, they produce 40% of all the GDP in the whole world. And then you have the US. The US produces sort of a 25 or 26% of GDP of the whole world. That is really, really good for a fairly small amount of people. What is it, 360 million, something like that. And then Europe with 450 million only produce 13% of global GDP. And that number is going down really fast. So we will be down below 10% soon. This is not
Wow.
good.
Yeah. Well, I love that you're positioning yourself well to have a technology to help turn that around once people wake up, right? Yeah, we're here to help. Yeah, and I'm sure that a lot of listeners will be happy to help too. I'd view it as an investment opportunity, right? And if enough of the red tape gets cut, then I'm going to be making stickers that say frack France.
But hey, this technology that we are making, we've said that from day one, not only me, but all the founders. This technology is not for just one country. This technology needs to get out into many countries around the world. And of course, as a company, we have to search for those countries that are willing to make it happen sort of a little bit faster and not take 10 years. So we will deploy in those countries where we get a fast route to deployment or commercialization. And then as it gets more and more into more and more countries, then hopefully some of the countries that were not selected in the first 5 or 10, then they will change their rules and make it a more easier to get it installed there. And I mean, there's 200 countries in the world, and I'm sure some of them will probably have to wait 100 years to get access to this technology. And honestly, we can only provide this to 5 or 10 countries in the beginning. So of course, not all countries can get this technology, and those countries who get it first, they will have a competitive edge, a very strong competitive edge. It's a little bit like having cheap gas, like in Texas. So yeah, let's see who it is.
I love it. Well, Thomas Jam Pedersen, thanks so much for the time. It's been wonderful to chat with you. I've been wanting to do this for a long time, so I'm stoked that we finally got you on the podcast. So we'll have to have you back to have updates. Best of luck with fundraising, and yeah, excited to see you guys progress. So
Yeah, thank you, and thank you for having me. Have a great night.